Welcome to Networks and Distributed Systems, a course based on the textbook by Jim Caros and Keith Ross, Computer Networking, a Top-Down Approach. This is our 15th lesson, and we have been discussing the TCP/IP model of network communications. Starting from the top down, we had an introduction module, and then we had a module on the application layer, the transport layer, and now we're into the network layer of the TCP/IP model. In the last lesson, we were introduced to hierarchical routing, and this lesson we're going to begin our discussion of specific hierarchical routing protocols, Routing Information Protocol, RIP, and OSPF, Open Shortest Path First Protocol. So let's get started. Having studied Internet addressing and the IP protocol, we now turn our attention to the Internet's routing protocols. Their job is to determine the path taken by a datagram between source and destination. An intra-autonomous system routing protocol is used to determine how routing is performed within an autonomous system, that is, a system under a single administrative authority. Intra-autonomous system routing protocols are also known as interior gateway protocols. In fact, that is probably the most common term, interior gateway protocols. Historically, two routing protocols have been used extensively for routing within an autonomous system in the Internet: the Routing Information Protocol, RIP, and the Open Shortest Path First Protocol, OSPF. A routing protocol closely related to OSPF is the IS-IS protocol. We'll first discuss RIP and then we'll consider OSPF. RIP was one of the earliest interior gateway protocols and is still in widespread use today. It traces its origins and its name to the Xerox Network Systems architecture. The widespread deployment of RIP was due in great part to its inclusion in 1982 in the Berkeley software distribution version of Unix supporting TCP/IP. RIP is a distance vector protocol that operates in a manner very close to the idealized distance vector protocol that we examined a couple of sections back. The version of RIP specified uses hop count as a cost metric. That is, each link has a cost of 1. Costs are defined between pairs of routers in distance vector algorithm described in the text. However, in RIP and in OSPF, costs are actually from source router to destination subnet. RIP uses the term hop, which is the number of subsets traversed along the shortest path from source router to destination subnet, including the destination subnet. In this figure that we have on our screen, we have an autonomous system with 6 leaf subnets, U, V, W, X, Y, and Z. The maximum cost of a path is limited to 15, limiting the use of RIP to autonomous systems that are fewer than 15 hops in diameter. Remember that in distance vector protocols, neighboring routers exchange distance vectors with each other. The distance vector for any one router is the current estimate of the shortest path distances from that router to the subnets in the autonomous system. In RIP, routing updates are exchanged between neighbors approximately every 30 seconds using an RIP response message. The response message sent by a router or host contains a list of up to 25 destination subnets within the autonomous system, as well as the sender's distance to each of those subnets. Response messages are also known as RIP advertisements. Consider the portion of an autonomous system shown here. In this figure, lines connecting the routers denote subnets. Only selected routers, A, B, C, and D, and subnets, W, X, Y, and Z, are labeled. Dotted lines indicate that the autonomous system continues on. In other words, the autonomous system has many more routers and links than the ones that are shown here. Each router maintains an RIP table known as a routing table. A router's routing table includes both the route's distance vector and the router's forwarding table. This slide also shows the routing table for router D. Note that the routing table has three columns. The first column is for destination subnet. The second column indicates the identity of the next router along the shortest path to the destination subnet. And the third column indicates the number of hops or subnets that must be traversed, including the destination subnet, to get to the destination subnet along the shortest path. For this example, the table indicates that to send a datagram from router D to destination W, the datagram should first be forwarded to a neighboring router A. The table also indicates that the destination subnet W is 2 hops away along the shortest path. Also, the table indicates that subnet Z is 7 hops away via router B. In principle, a routing table will have one row for each subnet in the autonomous system, although RIP version 2 allows subnet entries to be aggregated using route aggregation techniques. Let's next consider a few of the implementation aspects of RIP. Remember that RIP routers exchange advertisements approximately every 30 seconds. If a router does not hear from its neighbor at least once every 180 seconds, the neighbor is considered no longer reachable. Either the neighbor has died or the connecting link has gone down. When this happens, RIP modifies the local routing table and then propagates this information by sending advertisement to its neighbors. A router can also request information about its neighbor's cost to a given destination by using RIP request message. Routers send RIP request and response messages to each other over UDP using port 520. The UDP segment is carried between routers in a standard IP datagram. The fact that RIP uses Transport Layer Protocol UDP on top of a Network Layer Protocol IP to implement network layer functionality, a routing algorithm, may seem rather convoluted. Looking a little deeper at how RIP is implemented will clear this up. This figure sketches how RIP is typically implemented in a Unix system. For example, a Unix workstation serving as a router. A process called routd, although that's spelled R-O-U-T-E-D, is pronounced routd, executes RIP. That is, it maintains routing information and exchanges messages with routd processes running in the neighboring routers. Because RIP is implemented as an application layer process, albeit a very special one that is able to manipulate the routing tables within the Unix kernel, it can send and receive messages over a standard socket and use a standard transport protocol. As shown, RIP is implemented as an application layer protocol running over UDP. Like RIP, OSPF routing is widely used for intra-autonomous system routing in the Internet. OSPF and its closely related cousin IS-IS are typically deployed in the upper tier ISPs, whereas RIP is deployed in lower tier ISPs and enterprise networks. The open in OSPF indicates that the routing protocol specification is publicly available. Cisco's EIGRP protocol is proprietary. OSPF was conceived as the successor to RIP and as such has several advanced features. Basically, however, OSPF is a link state protocol that uses flooding of link state information and a Dijkstra least cost path algorithm. You recall that RIP was distant vector. With OSPF, a router constructs a complete topological map of the entire autonomous system. The router then locally runs Dijkstra's shortest path algorithm to determine a shortest path tree to all subnet with itself as the root node. Individual links are configured by the network administrator. The administrator might choose to set all link costs to 1, which achieves minimum hop routing, or might choose to set the link weights based on inversely proportional link capacity to discourage traffic from using low bandwidth links. OSPF does not mandate a policy for how link weights are set. That is the job of the network administrator. Instead, it provides the mechanisms or protocols for determining least cost path routing for the given set of link weights. With OSPF, a router broadcasts routing information to all other routers in the autonomous system, not just to its neighboring routers. You remember how a link state algorithm works. A router broadcasts link state information whenever there is a change in the link's state, such as a change in the cost or a change in up-down status. It also broadcasts the link state periodically, at least once every 30 minutes, even if the link state has not changed. According to the specification, this periodic updating of the link state advertisements adds robustness to the link state algorithm. OSPF advertisements are contained in OSPF messages that are carried directly by IP with an upper layer protocol of 89 for OSPF. The protocol numbers are managed and assigned by the Internet Assigned Numbers Authority, IANA. Therefore, the OSPF protocol must itself implement functionality such as reliable message transfer and link state broadcast. The protocol number is found in the header and defines the format of the header that immediately follows the IPv4 or IPv6 header. The OSPF protocol also checks that links are operational and allows an OSPF router to obtain a neighboring router's database of network-wide link state. Some of the advances embodied in OSPF include the following. For security, exchanges between OSPF routers can be authenticated. With authentication, only trusted routers can participate in the OSPF protocol within an autonomous system. This prevents malicious intruders from injecting incorrect information into router tables. By default, OSPF packets between routers are not authenticated and could be forged. Two types of authentication can be configured: simple and MD5. MD5 is discussed in Chapter 8 of your textbook. It's not likely that we'll get that far in this course, so take a look at it on your own. That chapter discusses MD5 and authentication in general. With simple authentication, the same password is configured on each router. When a router sends an OSPF packet, it includes the password in plain text. Clearly, simple authentication is not very secure. MD5 authentication is based on shared secret keys that are configured in all the routers. For each OSPF packet that it sends, the router computes the MD5 hash of the content of the OSPF packet appended with the secret key. Then the router includes the resulting hash value in the OSPF packet. The receiving router, using the pre-configured secret key, will compute an MD5 hash of the packet and compare it with the hash value that the packet carries, therefore verifying the packet's authenticity. Sequence numbers are also used with MD5 authentication to protect against replay attacks. OSPF uses multiple same cost paths. When multiple paths to a destination have the same cost, OSPF allows multiple paths to be used. That is, a single path need not be chosen for carrying all traffic when multiple equal cost paths exist. Multicast OSPF provides simple extensions to OSPF to provide for multicast routing. MOSPF, as it's abbreviated, uses the existing OSPF link database and adds a new type of link state advertisement to the existing OSPF link state broadcast mechanism. Perhaps the most significant advance in OSPF is the ability to structure an autonomous system hierarchically. An OSPF autonomous system can be configured hierarchically into areas. Each area runs its own OSPF link state routing algorithm, with each router in the area broadcasting its link state to all other routers in that area. Within each area, one or more area border routers are responsible for routing packets outside the area. Lastly, exactly one OSPF area in the autonomous system is configured to be the backbone area. The primary role of the backbone area is to route traffic between the other areas in the autonomous system. The backbone always contains all area border routers in the autonomous system and may contain non-border routers as well. Inter-area routing within the autonomous system requires that the packet be first routed to an area border router, then routed through the backbone to the area border router that is in the destination area, and then routed to the final destination. Well, that concludes our discussion of interior gateway protocols, RIP, and OSPF. We're about to go into the border gate protocol, so this is a good place for us to stop. Take a look at your notes, maybe review the video again if you need to, update your study guide, and when you're ready, come on back and we'll do the next one.